I doubt I'll get to the right-hand side. I'll have to come back to the right-hand side and give you vectors in 3 dimensions. I'm going to hit the left-hand side in 2 dimensions. Are you ready? There are many little skills here, none of which are hard, but there are many little skills. So, and some of it is vocabulary. So, a vector is a quantity with both direction and magnitude. Too bad I didn't show the video, I don't have time. Okay, a vector can be expressed 3 different ways. There's actually 2 component forms. Both consider right-left movement versus up and down movement, where right-left comes first, just like x and y in a coordinate plane. X comes first, y comes second. Same with here. In terms of notation, many books use bold for a vector. It's hard when you're writing, though, to make it bold. And so we will not use bold notation for vectors. We will use this notation. We use this notation for vectors. But either way, those horizontal components could be written one of 2 ways. I hat, J hat, or what I typically call component form. It's got these pointy parentheses. Make sure they're pointy, not rounded, so it doesn't look like a point, okay? Pointy parentheses. But in both cases, they're horizontal, vertical. You follow? Okay. We can also do a vector in polar form, which is to say r at an angle of theta. Our book uses degrees. We will typically use radians. Other textbooks are a bit of a mixture also, so it's good to know. Okay. In any case, though, if there is no degree mark, then it's assumed to be radians you're looking at, not degrees. You follow? Okay, magnitude. Other notes, magnitude. What is magnitude? Yeah, it's the size. It's the length of the vector. You will often hear it called the norm of the vector. You'll see those 3 used all interchangeably. In terms of notation, it is one of 2 notations. You'll either see a single line, which looks like absolute value, and that's unfortunate because it is not absolute value, but more common is double. When you see double bars on either side, that is the length of the vector. You can find it by, well, it kind of depends on if it's polar or rectangular. If it's polar, if I say 2 at an angle of 70 degrees, then if that's angle or vector u, then the magnitude of u is really easy to find. What is it? 2. It's just the length of the vector. If, however, I give you component form, u is 2 horizontally and 3 vertically, then the magnitude is found by Pythagorean theorem, Spartan 13 in this case. You follow? In both cases, the magnitude or the norm is a scalar. It's just a number. It's not a vector, with a component, a direction. It's just a number. It's how long it is, period. Okay? A scalar is just a plain number. Often you'll see scalars or plain numbers thrown in conjunction with vectors. For example, you might see a scalar multiple of a vector. If I gave you vector u, and then I asked for what's 3u, then 3 is a scalar. It's just a plain number used with vectors. And it's stretching the vector out in both directions by a factor of 3. So 3u would be negative 12, 15. If I used I hat, j hat, then it would have been negative 12 I hat plus 15 j hat. Again, those both are used to show horizontal vertical movement. You follow?
What was the I don't know what they're called, the triangle things they're using on the side to represent a set of parentheses. Like you see.
Oh, these are vectors. If you use this, it implies vector, not point. That's pointy. Okay? Vectors component form uses pointy parentheses. Okay, in 3 dimensions, I'll just throw out here, in 3 dimensions, it's I hat, J hat, and the 3rd dimension is K hat. Okay, drawing that is way more fun. We'll get to 3 dimensions later soon. But for now, let's focus on drawing 2. Okay, so when I draw, first of all, it's not necessary to start at the origin. If you say otherwise, you can start it any which way you want. So for example, if I wanted to draw -4, 5, I could start at the origin and go 1, 2, 3, 4 left and 1, 2, 3, 4, 5 up, and I could say that's U. But there is no reason I couldn't start here and say 1, 2, 3, 4, 1, 2, 3, 4, 5, and that's U. Or I could start here and say 1, 2, 3, 4, 1, 2, 3, 4, 5. All those could be vector U. Now, typically, we assume, starting from the origin in most cases, unless they say otherwise, but it really can be anything. You follow? All right. Now, sometimes they nail it down to a single point by giving you initial and terminal points. Initial obviously being the starting point of the vector, and terminal being the ending point of the vector. For example, if I told you that point P, which is 2, 4, notice those are rounded parentheses. These are points, not vectors. 2, 4 is a point in space. 4, 1 is right 4 up 1. That's a point in space. Here's P, here's Q. If I went from P to Q, then this here with direction is vector P, Q, or you could also read it as P in the direction of Q. To get from P to Q, what horizontal and vertical components did I use? In going from 2 right to 4, I went 2 units horizontally. And going from 4 down to 1, I went -3 vertically. Now that was direction. That was a vector, so this is components form. Or you could say 2I hat minus 3J hat is fine. That's P in the direction of Q. What would Q in the direction of P be? Or QP, vector QP? It'd be from 4 to 2, so that's -2, and from 1 up to 4, +3, if you -3. In every case, then, if you have generally, if point P is P1, P2 for its X and Y, and point Q is Q1, Q2 for its X and Y, then PQ is found by taking differences. Q minus P or P minus Q? Q minus P, it is vector. Q1 minus P1 for the horizontal component, and Q2 minus P2 for the vertical component. You take away end minus start. End minus start gives you the vector. You follow? Okay. If you get one form, you should be able to convert to the other. For example, 4 at an angle of 2 radians. What quadrant is 2 radians in, my friend? Second quadrant. It's between pi over 2, which would be about 1.57 radians, and pi, 3 radians. So it's probably in here somewhere with a magnitude of 4, yeah? You're trying to find the R, or the I hat component, and the J hat component, the horizontal and vertical components that get you there. Unlike Algebra 2, you don't have to draw the picture, you don't have to do much, you can just say straight up that it is what I hat. How do you get the I hat component, which is adjacent? Cosine. It's like x in polar, right? What was x in polar? X is r cosine, because it's adjacent, theta. And y is r sine theta. Well, I think I always use this in my mind when I was your age. Cosine and sin. Cosine I and x, they all go together. Sine j and y, they all go together. So if I want the horizontal component, the I component, then I'm using cosine, and it is 4 cosine 2 for the horizontal, and for the vertical it's 4 sine 2. Cool? Then you can just leave it like that. All right.
Why is it at 2? Why?
2 is not this angle. When I give this is the polar angle. It's the angle starting from the x-axis to the terminal side. So I don't need to do any playing with it. When I do, it's kind of like if I did cosine of 120. Do I need to anymore say, well, the related angle is 60 and let me attach the appropriate sign, or is it all in there? It's all in there, you know what I mean? You don't know what I mean.
No.
Okay?
Like, how does,
So if I said cosine of 120, do you draw the triangle? Do you say, oh, pi, do I say 180 minus 120 and that's 60 and now I'll do a 60-degree angle and then I'll put a sign under? Or do you just say cosine of 2?
but you need the inside angle, not.
What, you need this angle? No, this is what I want. I want the cosine of 120. Isn't that there?
But to find the, again,
So, okay, good. I see what you're saying, but let's first of all here. Cosine isn't cosine even, first of all. So cosine is going to know, it's going to be the same 120 versus 60, and we already know the sign in there, yeah?
no, but you're like subtracting it mentally. Like you're knowing that cosine of 120 is equal to 60.
I
You
s-
don't know what the other.
That's I suppose that's true, but the calculator and you know that cosine of one. Wow, I didn't think we would have trouble with this. I gotta figure out how I taught algebra 2.
Oh. No.
I'm saying you're way
Okay,
overthinking.
the 4 cosine of 2, that's your I hat. Or is it not?
4
your I
cosine
hat?
of 2 is the ice.
It's your
Yes.
I
So
hat.
think of it like this. I guess you could say, isn't this? I mean, I guess I could think of this as. This is pi minus 2, and I could take the cosine of pi minus 2, and that's adjacent over 4, and then I have is 4 cosine of pi minus 2, and all that.
So then why is that just a 2 then? That's what I don't.
Why is this the same as 4 cosine of 2?
Yeah.
Okay, fair enough. Cosine of pi minus 2 is equal to cosine of 2, yeah?
Wait, shouldn't it be
Sine of, oh, wait a second, what'd you say, Al?
negative cosine of pi minus 2?
Oh, yes, then you would have to say, you're right, this would be the negative I hat, right? That's a negative I hat, and so you would say it's the opposite of.
Okay.
So I guess you could do all that. You could do, in Algebra 2, we did related angles, we attached the sign, and all that stuff.
Yes.
Okay, but we know that cosine of 120 is the opposite of cosine of 60, and cosine of 150 is the opposite of the cosine of 30. And so, rather than do the negative and the related angle, we just do the angle.
Okay.
Yeah. Okay.
Yes.
Okay. All right. Okay. Cool. Converting into polar, negative 4, 5. If I were to draw this, which you don't have to do, but I do, negative 4, 5 is in the second quadrant. Yeah. You can find r by Pythagorean theorem, which is 16 plus 25 root 41. Yeah? For the theta, I first find the related angle with no sign. I say theta is the inverse tangent of 5 over 4. I do not use the sign. It complicates the thing in my mind. I just find the related angle, basically just pretending it's like a triangle in space. And then I figure out what the actual polar angle is by considering the quadrant. If the angle is in the first quadrant, then the polar angle is just straight up the inverse tangent, yeah? Which, by the way, is inverse tangent of j hat over I hat, the opposite over the adjacent. If the angle is in the second quadrant, then theta is pi minus the inverse tangent because it's a little less than pi. If it's in the third quadrant, it's a little more than pi. So theta is pi plus the inverse tangent of the related angle. And if it's in the fourth quadrant, you could go one of two ways. What's one way to get that angle? Never 3 pi over 2. You never use the vertical. You use only the horizontal. So 2 pi minus the inverse tangent. Could you also just do minus the inverse tangent? To go straight down. Okay. So all those are cool. In this case, then it would be theta would be pi minus the inverse tangent of j hat 5 over 4. Whichever is that, I get something like root 41, that angle, whatever it is. Okay? Okay, now let's get to drawing and adding vectors, arithmetical vectors. It's really easy to add two vectors when they're in component form. You just take the total horizontal, the total vertical. What's the total horizontal movement?
6i.
6ix. And what's the total vertical?
-2.
Negative 2j hat, okay? So when you add in component form, you just add the components. Now, in terms of drawing this, you commonly don't just draw the result, but you draw the relationship between all three, the two vectors that came together to make this combination vector. And in doing so, there really are two methods to go to that. If you draw the parallelogram method, and when you draw u, it's right 2 up 3 from the origin. You can draw v from the origin, which is right 4 down 5. Now, the parallelogram method is I'm going to draw the combination of the two vectors. Imagine if this is two sides of a parallelogram, then this side would mirror that side, so look like this, and this side would look like that, yeah? This diagonal of the two vectors, this is u plus v. And doesn't it look like right 6 down 2? Okay, so one way is to draw both from the origin, make a parallelogram. The diagonal of the parallelograms is the sum vector. The other is the head-to-toe method, or the triangular method, where you draw the first one and then draw the next one from where the first one left off, kind of making a new origin. So I could go 2 and up 3, and that vector is u. Now you're imagining a new origin at the head of that guy, and now I'm going to do v. From there, I'm going to go right 4 and down 5. That's v. That's v. And then the combination of those two, where you end up, is the sum u plus v. You can see it also is right 6 down 2. Cool? Now the unfortunate is it's really easy to add in rectangular, but not in polar. Can you add these two? No, you can't. All right. I will finish this tomorrow. If you didn't pick up set 107 yesterday, pick it up. Anything you can do it tonight and have it done tomorrow. Anything I haven't